Okay, we start up. So today I'm going to talk a little bit about how you can extract data from OpenFOAM and then make plots in other software like MATLAB, for instance. So it's a little bit messy, but something you have to know anyway. You're going to need this. Before we start with that, I wanted to show you then the exercise 3, which now should be out, looking something like this. So here you have your first report exercise, and your job then to simulate turbulent flow, steady state, incompressible through a pipe, which then have a sudden expansion and a sudden contraction. And here is the aim sort of for your report. And this is what I'm going to look after when I do the grading for each report. That you have both understood and you can use turbulence models. Of course, we're only operating in the RAS family, 2 equation models typical. Y plus, low of the wall, turbulent boundary conditions. I mean, these are sort of connected. You should know that by now. And also the grid convergence index. At the end of this file, you have been given here a block mesh dict, so we'll have a look at that one a little bit later. But here you sort of have a visualization of what this mesh, how this mesh actually looks. So it's a thin piece of cake through the entire, say, pipe system. So here you have then the symmetry line, and then you have the top wall here. And then we had the expansion on the top wall, and then a contraction on the top wall, and then finally the outlet. So how to make such a mesh, that's why I've given you this recipe. And yeah, as a hint here, this is important. You have to calculate the positions here for the different blocks. It consists of 4 blocks. And the position there has to be punched in with plenty of digits. As you can see, I've done it here. Corner number 0, corner number 1. So I just used format long in MATLAB and then calculated the positions, cut and paste. So you need plenty of digits. This is overkill, I guess, but at least 18 digits. Or else the block mesh or the check mesh, they won't accept the mesh. It's going to crash. So you have to be quite accurate when specifying the different positions. Totally your choice with what Reynolds number you want to look at. Of course, in the turbulent range. And also what kind of dimensions you choose for your pipe. Radius or diameters and different pipe lengths for the different sections. Totally up to you. But other choices that you make, and there are many of them, you sort of have to give an argument. Why have you made this choice? Like what turbulence models to use, whatever. So you sort of have to argue all the time that yes, we done it like this because so and so. So it must be justified. You can't just say, okay, we have one setup for a simulation here, done. You sort of have to argue for all your choices that you have done for the setup. Here you don't really need any arguments. Well, it may be a little bit question about, say, the pipe lengths, because you have something you need to address here, something called an entrance length. So that's something you have to look at. because the flow should be fully developed when you start here at an inlet and then you hit the sudden expansion. So at this point the flow should be fairly fully developed. And then he's going to mess around a little bit, and then before he hits the contraction, again there should be fully developed flow. And also at the outlet, fully developed. So the pipe lengths may have to be adjusted. Of course, the choices I made here are totally insane. This won't work at all, no way. And also each block has only 5x5 cells. Totally crazy. So, of course, from the basic fluid mechanics courses you've been through, yes, you should know about this, major and minor losses in a Bernoulli, and when you compare, then the pressure distribution then along the symmetry line, yeah, you should have a sort of a match with, say, classic, well-known engineering theory with the Bernoulli with losses. I need one PDF file, and for the different groups here, it's enough that one person in the group uploads the report. That's okay, that's enough. But please make it as one single PDF file, everything into that one. And yes, you don't have to write a decent report or anything like that. Must be readable, of course, or understandable. But no, you don't have to write full sentences, and you don't have to have a table of contents or any stuff like that. Make it easy. So for instance, the way I wrote solution to exercise 2, you can use that one as a sort of an idea how such a report may look like. Let's have a little bit look at such a mesh system when we come to what's called a wedge. This is this piece of cake when you want an axisymmetric 2D simulation. Yeah, I specified some corners. And here I now have 4 different blocks. And each block has 5x5 cells in, say, now it's going to be the radial direction and the axial direction. Nothing happens in the theta direction. But if you look at the organization here for the different corners, it's a little bit strange. Some of these corners, they appear twice. So that's a little trick how this is constructed. So I'll show you later. And also, you're going to need to specify the position for some of these edges. So I just chosen very easy here, very crudely, the radius of 1 meter and radius of 2 meter for the thick pipe. But here you may have to do some decent calculations, big numbers or long numbers, to get it precisely. So let's have a look at how such a mesh can be constructed. Any questions, by the way, before I remove this one? That's okay. Deadline next Friday. Okay. So I have constructed the mesh as follows. Say here we have a symmetry line, something like that. And then we start here sort of with a thin piece of cake. Let's overdo it a little bit. So it should be something like that. This angle, by the way, should be small. Should be smaller than 5 degrees. I'll use 4. So to evaluate, well, we can draw the rest first. Let's see now. should be something like that. And then we have the big pipe coming up here. Something like this. And then we go down, and then we continue here. Let's see now, and then we finish us off here. So here you have sort of the mesh system. Should be like that, and this one should go all the way down there. There we have it. So to evaluate the different corners, yes, you have to use a calculator or MATLAB or something. So what I did, I said, this is corner number 0, location 0, 0, 0. I started with that corner. And then I had corner number 1 and corner number 2. Here I have corner number 3. And here I had corner number 4 and number 5, number 6, number 7, and inside here number 8. And then I had 9, 10, and 11. And then finally the top here, 12, 13, 14, and finally 15. Now constructing a wedge. Say take the first block here, for instance. Then we are going to use 0 and 3. We're going to use them 2 times. So to construct a block, I now say I start with 0 to 3, go up to 5, and back again to 2. Then I sort of have the back plate in this first block. And then I need the front plate. But then I sort of use 0 and 3 again. 0 and 3, and then finally 4 and 1. So that's sort of the logic here. Normally you would have a block where you had 4 points downstairs, but we sort of reuse 0 and 3 just to sort of make a wedge out of it. So that's the philosophy. And now the same goes with the other blocks. Of course, this one is also split, something like that. So I have 1, 2, 3, 4 blocks. Yeah.
Does it matter if you do the back before the front, or which before the back, or is it something with the coordinate system? Or,
yeah, it is something with the coordinate system. So yes, you should do the back first and then the front afterwards, just to be safe. I haven't tried it the other way. It may work. I don't know. Be my guest.
So always the back before the front. You can use that as a rule.
Yeah, it works. And also later, when you have to identify the different faces, then, as always, right-hand rule. So say the face for the front here, it will be 0, 3, 4, 1. Then you have a normal vector on that face pointing out. On the back face, you should then go the other way, 0, 2, 5, 3, and he will point the other way. And now this face here, well, he is a little strange, isn't he? He will be 0, 1, 2, and then back to 0 again. So you will have 0 twice. Why not? So that is sort of how we operate such, say, meshes. And then, well, the same logic then should apply with these two. The top block here, well, he has actually the normal 8 corners, so no change with him. That shouldn't matter. But for the edges, yes, you have to do that one as well. Edges. because this line here between 1 and 2, that's not a straight line. It should be part of the cylinder surface. Hence, it should be an arc. So you have to put an arc here between point 1 and 2. And how do you do that? Well, then you use an arc and you state from 1 to 2. So it should read something like this: arc from or between point 1 and 2. And then you need to specify a point. A point, he already knows these 2 points. You just have to specify a point on a surface here. So I did it very, very easy. Think of this as the y-axis, like that. And then I had a radius of 1. So the y distance here is 1. X is 0, and the z direction also 0. So the location of that point should then be 0, 1, 0. And I think that's what I did here. Let's see. Yeah. So actually it's written like this: arc, and then a number, and then the location 0, 1, 0. If you choose a different radius than 1 meter, of course this one then has to be changed. So again, use enough digits if you have not just 0.5 or 0.2 or 0.1 or something. It has to be precise, or else you will have an error. And then you have to do the same then between 4 and 5. He's also an arc. 7 and 8, 10 and 11, and also up here between 12 and 13 and 14 and 15. Here you also need to specify an arc point. Here I had a radius of 2 meters. So as I said, I chose completely insane dimensions here. 1 meter and 2 meter in radius, and then 3 meters long or something stupid like that. Yeah.
Are we going to create this mesh ourselves, or have you created it?
You have in the task, you have this block mesh written out with this mesh. So you may use the exact same logic that I have. That's quite easy, so you don't have to change anything there. The only thing you have to worry about is the dimensions. So the location of the different points, how long should the pipe be, what's the radiuses, and then calculating these numbers correctly. So, but you can use this, the same setup. Other questions? So here you see first arc between point 1 and 2, location in X, Y, and Z. So I had a radius of 1. But here, say the point number 2, for instance, well, he's fairly close to 1. So this will be cosine of 2 degrees. And this will be sine of 2 degrees. And then point 3, 0, 1, 2, point 2. The same height, of course, in the y direction, but then a negative in the z direction. So that works. Okay, if you have any question on this, of course, we have exercise hours, so you just ask me, of course, no problem. Anything else you are wondering about with this exercise? That's okay? So I just organized it as an ordinary exercise. And you are allowed to, or you will be given a value between 0 and 100. And that's your grade. So when we have then, when we are done with all these exercises, I'll just create an average and you will have a grade in this course. Simple as that. Okay? No questions? Then, then let us jump to the OpenFOAM, and I want to sort of extract the data from an OpenFOAM case. I'm going to need this data because I want to now make some nice plots in, for instance, MATLAB, Python, GNU plot, whatever you want. But I mean, you need the data and how to achieve them. So as a first test here, let's use the cavity case. Let's just make a very small one for simplicity here. So the square cavity case. Here I now say I have 5 by 5 cells. Why not? Just to do it easy. And then save that one. And let's run this case. Block mesh. And this was OpenFOAM. Like that. So now I have a result. Everything fine. Have a look at it. Parafoam. And it should then look something like this. Say for the velocity, and we run to the end, and yeah, of course 5 by 5 cells, and also it's only half a second, so very bad solution, but never mind. Say now you want to, I mean, you don't like this figure, you want to have the data here so you could plot it the way you want it. Well, first option, you have the save data. Must be nice. Save data, and then you should choose here a format that should be readable for, say, humans and other software. So just the first one will be an ordinary ASCII file. So yeah, I choose that one. And then, no, sorry, comma or tab. You have to give him a name, whatever you want. Then he's asking precision. You may not need 5 digits, maybe it's enough with 3, but your choice. And here, normally I just click just OK on this one. And now done. Let's see what has happened. Well, I have a file here. It's called a.csv. Let's have a look at that one. Let's have a look at that one. In the cavity, a CSV. And then we open that one. Okay, so here I have a whole bunch of numbers. This one actually includes everything. If you look at the heading, the first line, he will give you sort of an idea of what is shown here. Points 0, 1, and 2, meaning X, Y, and Z direction. And then he has U, 0, 1, and 2. That will then be the velocity in the X, Y, and Z direction, and then finally the pressure. Of course, if you now had a turbulent case, for instance, oh, this one is going to be pretty long. You have a K, epsilon, U, and T, Y plus, I don't know. You can have a whole bunch of numbers here. But for this one, for the laminar case, not that many. And then, if you look at this file here, let's go all the way to the end. Where are we? No, we won't do that. Go all the way to the end. Does it make sense? Does it make sense? I had 5 by 5 cells. 5 by 5 cells. How many unknowns do I have then? I should have 25. I should have 25 lines here. I got 73. Thank you very much. What's happening here? What's happening here? Stupid OpenFOAM. He interpolates a lot. If you look at the points, that's the 3 first numbers here. So you start with 0, 0, 0. I don't have a point in 0, 0, 0. Do I? Let's have a look. So here is my mesh system. I just draw it 4 by 4 for simplicity. How does OpenFOAM operate? He uses co-located mesh systems. So here I have V velocity, U velocity, and the pressure. Everything located in the cell centers. So I should then have here, I would have 4 unknowns for pressure, for U velocity, and for V velocity, and nothing more. But he needs boundary conditions. So he also invents a point here, here, and here, and down here, and so on, all around the boundaries. These are for the boundary values. So yes, I have this one in addition. Fair enough. Shouldn't be that many, should it? Let's see now. If we had 5 by 5 internal points, then we have to add what? 5, 5, 5, and 5. What's that? That's 20. Then I should have 45 values. Still doesn't make sense, does it? I had 73. So what's really happening here? Sadly, what's happening is that OpenFOAM, he interpolates. The results you get are located now in the cell corners. This is what you get when you just save the data crudely. And that is not so good. I don't like that. I mean, when you are plotting something, of course it should be the original data that he actually has simulated and nothing more. But sadly, he then does this strange interpolation thing. Furthermore, he also takes the interpolation in the Z direction. Thank you very much. So the cell centers here, remember, it's always 3D. They will be in the center of each cell, also in the Z direction, in the center. But no, he has then from the back face and also the front page. Irritating. Very, very irritating. You can get the idea if you look at, say, the set positions here. Here they are 0, 0, 0, 0 all the way. But if you look at the bottom of the file, you get the exact same numbers, but now Z equals 0.01, meaning he gives you 2 different fields, but they are identical. One for set position 0 and one for set position 0.01. So you sort of have twice as much information here. That's that you don't. Well, you only need one of them. Of course, possible to load this entire file into MATLAB and then start interpolating back into the original positions, if you like. But then you have an interpolation of an interpolation, so that's not precise. So no, this is not a good way to do it. Possible, sort of straightforward, but I don't like it. What other choices do we have? Well, we have at least one thing in OpenFOAM that is not so stupid. Say now, let's have a look at the U velocity again. I want a velocity profile along a line here. Then that should be the x velocity. So I use plot over line. Specify the location here. X should then go 0.05. Y is 0. X should be 0.005 in the center. Again 0.05, 0.1, and then 0.005. There I should have a straight line in the center, a vertical line in the center of this cavity. And if you look at what you plot, you get U magnitude by default. I don't want that. I want U. Away with that one. And also, I don't need the pressure here. That's all important. I want that one. There you have the velocity profile. Starts with 0, goes negative, and then big 1 at the top, of course. So not so stupid. I want the data for this curve. And then again, with this plot active here in the pipeline browser, if you now say save data, you get these data. You don't get only U. I think he takes everything, but at least you get at least one. But this will only be plot along one single line. But again, OpenFOAM interpolates, and here resolution is 1000. You get 1000 points. Totally overkill. I would actually just like to have my original data points and nothing more. Not 1000 points. That's unnecessary. I mean, it should be possible here to choose something at segment centers. Let's try that one. Yeah, should be better. You could also use the cell boundaries. Then he has interpolated to the cell boundaries. So your choice. But okay, let's try this one. File, save data, and we call that one B. Okay. B. Let's have a look at B. Should be created here. Yeah. Open B. So that one looks a little bit better, doesn't it? You have the velocities, U, V, W, you have the pressure, then you have something called VTK point mask, whatever that one is, and an arc length. Arc length, that is the distance accumulated from starting point to the end point. Whatever you need that one for, but at the end, X, Y, and Z. So this one looks actually reasonable. And you see now the set position is located where it should be, in the center. So this one will actually be more precise than just flushing down the entire field. So plot over line, yeah, that might be a good idea actually. But 1000 points by default, of course you can use it, but he just interpolates anyway. Okay, so far OpenFOAM. We have some other options here in OpenFOAM. You have something called sample dict. Let's find that one. Let's see now, where do we have our OpenFOAM here on this version? Echo, where are we? Foam tutorials. Yeah, should be under user lib on my computer. So if I now search for, let's see now, user lib, and then we had OpenFOAM. I can search the entire OpenFOAM structure, not just the tutorial, but everything. And I want to find a file, type F, with the name sample dict. So he found some in 2 tutorials, one RAS and one LAS. They have used this sample dict trick. And then also here under etc, they have a sort of a generic sample dict file. And that one contains a lot of information. Now I cheated. I think I copied it already here. Let's see. Yeah, I took a copy of that file. So let's have a look at it. Where are we? No. Gedit. Sample dict. This file, if you make a copy of this file and put it in your system folder, then whenever you simulate, he will automatically sort of do this. And what does he do? Well, first of all, you can choose the output, just a raw output, meaning straight as an just the data by itself. So actually possible here to create output formats so you can read it directly in different softwares. But raw, I would say that should be quite normal. I mean, this file here is pretty big. You don't need all of it by all means. But you have a lot of choices here, what you want to sort of extract from your result data. Format ASCII, I think that's default anyway, so I don't think you need it. But yeah, it should be ASCII, of course. And then here, what fields to sample? This is important. I mean, here I specify pressure and the velocity. So he will load that one into memory and then start, say, extracting data from these fields. And then you can choose a whole bunch of different things. Plot over line, plot phases, plot along any polyline, for instance. You can do whatever you want here. And as a simple example, they have here used just very simple here. Type uniform, that's a straight line. An axis, the chosen distance. You give the start and end points for your desired line, and then the number of points. So you have some examples here. And if you continue to look into this file, you're going to get a headache because you have a lot of options here. Normally, I would say you can stop already here. But I mean, you have the alternative as plot over line in ParaFoam anyway, so your choice. But here, if you look into it, you have a lot of options here. So this will be one way, say another way to do it. Just copy the sample dict file into your folder, and then when you simulate, he will automatically give you result files. Now, if we have a look at how this one is done, on my system here, when I searched for the name sample dict, I found 2 different tutorials. So if we take, for instance, this one and see what they have done, we can do that. I just flushed that one out on the screen. Cat, and then the entire address, something like that. Copy that one. And then I write bar and more. That's a nice way to flush a text file on the screen. Cat file name. And then when you use such a pipe and write more, he will give you one page at a time. So let's try it. Oh, I need enter first, thank you. So here's the start of this file. So you see they have removed a lot of all this information from this generic sample dict file. Raw format, and then interpolation, they use cell points, that's okay. What fields to sample? Oh, you see this is something to do with chemistry. So you have a lot of different fields here, never mind that. And then they have some center line, type uniform, that was a straight line. Start and stop, start and end, and then number of points. And then they have several of these lines. And that's it. So that's one example, at least on my version, how such a sample dict may look like. And for that tutorial, you just put this sample dict inside your system folder. That's all you need to do. Then he will automatically give you these results. Okay, we have another option, more advanced. We will do that one after the break. Any questions?